In this chapter, we'll look at potash as it enters the subsurface and how it reacts at various times during its mesogenetic history. Now, potash is one of the most reactive, be it sylvite or carnallite, it's one of the most reactive mineralogies in the evaporite suite. What we tend to see with potash is varying combinations of primary, secondary, but also multiple overprints and alterations that can take place via incongruent dissolution and pervasive recrystallisation in the subsurface. Now, there are certainly some ancient potash ores that retain their primary precipitate texture, and this is especially so when we look at neogene ores. The Navarra potash, for example, shows excellent preservation of the depositional architectures, including the halite reefs separating the potash lamanites. And we look at that in a lot of detail, along with all aspects of potash geology in our potash evaporites course. This is a summary of some of the broad discussions that we make in that potash course. Some potash ores do retain their primary laminar chevron alternating with sylvite depositional laminae. But in others, we see much more pervasive secondary textures and overprint, and this is especially so as we go further back into the rock record. Some potash cores, even the Devonian in Canada, retain evidence of syndepositional karst fields, especially in the carnallitic sections where we have combinations of carnallite and halite. We also see during its mesogenetic history extensive burial replacements of the potash ores, often associated with incongruent transformations from carnallite to sylvite. They can be multi-stage in the burial environment. We can also see evidence eogenetically of meteoric replacement of potash, but much more pervasively as the potash ore starts to re-enter the telogenetic environment. Potash, like halite, because of its very high solubility, rarely makes it to the surface in the telogenetic realm. If it does make it to the surface, it will be enclosed as disaggregated clusters within Namakea halite. There's an example on the right showing us the typical Salado formation ore from the Delaware Basin in Texas, where we see a combination of sylvite, halite, polyhalite, very little, if any, primary texturing preserved in that sample. And that's because potash salts are highly reactive. They are one of the most reactive of the evaporite suite, secondary to bischofite, but still much more reactive than halite. So we tend to see very early syndepositional eogenetic alterations of the primary salt textures, quite often via back reactions where we see reactions with residual primary liquors as we see those brines sinking down through the underlying succession. Remember that these are prograde salts, so with cooling they tend to saturate. Unlike anhydrite, the retrograde salt, with cooling it tends to go into solution. So in the burial realm, the mesogenetic realm, we see pervasive alteration of potash minerals. Quite often this is happening in environments where we are seeing relatively tight surrounding evaporite units, but remember also that with a gypsum association, we will see a flush of structural water coming off that gypsum as we dewater it into anhydrite. Now, due to the heat conductive nature of salts, quite often temperatures within our shallow buried sediments, the evaporites, can be much lower than if they were at the seawater interface. Once again, this is the case where we're looking at cooling, especially if there were helothermal bottom waters, we see cooling driving the precipitation of those potash minerals in the eogenetic realm. And then we can see retrograde alteration of the evaporite minerals, as we talked about with gypsum, with that pulse releasing that flush of water. So we have a source of brines, both via prograde reactions with cooling and saturation in both halite and sylvite, or halite and carnallite. And then we can see incongruent versus congruent dissolution. Much of the sylvite that we see in the subsurface is interpreted as the result of the incongruent alteration or solution of carnallite. With incongruent alteration, we're talking about the dissolved solute transforming, in the case of carnallite, by a loss of magnesium chloride and water into sylvite. With incongruent alteration, or dissolution, reprecipitation, the dissolved solute does not stoichiometrically match its precursor. What we see is a salt going into partial dissolution, and we leave behind a new daughter product. In this case, it's carnallite. Remember, that's potassium magnesium chloride hydrated. We're losing the magnesium chloride and the water, and we are leaving behind as an incongruent product the sylvite. Whereas halite, which tends to dissolve via congruent dissolution, as does sylvite, we basically have complete leaching of that product. We leave behind moldic porosity, which can then be filled by a later mineral phase. Much of the texturing we see in sylvite implies that it is an incongruent dissolution product from carnallite, and we look at those textures in detail in the potash course. We can also see evidence of early preservation of structuration in many potash ores. These are taken from the Delaware Basin, but you see similar things in the Lanigan mine in the Devonian potash in Canada, where we see these dissolution pipes, these clay-filled dissolution pipes. Those dissolution pipes can also be filled, as we see in the case of the Devonian of Canada, with carnallite within a halite matrix. This is implying that this is a prograde product by the descending of brines into early formed syndepositional karstic pipes. We see this in intercrystalline positions. We see it much broader in pipes, 5 centimeters across, as we're seeing here in the marker bed 118. Notice that those pipes are directly below that freshening event. That's implying there must have been vadose exposure. That's a gravitational feature. It's vertical. To get gravity doing that and creating karsting, we need to have lowered the water table. Pipes, as I said, can be filled with carnallite or they can be filled with clay. It varies. But there's good evidence in many of the potash deposits around the world of this type of early eogenetic structuration. And it's quite interesting that when we look at potash, there's quite often a much clay association than we see with halite or gypsum in large evaporite basins. Quite often the potash component in our ore is associated with insolubles and with clays, once again implying that there was a dissolution reprecipitation process taking place, building up the levels of carnallite in hyper-arid situations with eogenetic potash precipitation. We'll follow this up a little later when we look at climatic associations, and we'll see that if we look at the giant potash deposits around the world that are being exploited, most of them are associated with hyper-arid hothouse earth conditions. But then let's look at what happens in the subsurface. In the subsurface, we can create mesogenetic sylvite. And that's because as we bury the system, the pressure increases, that's on the vertical axis in this diagram, and the temperature increases, that's on the horizontal axis in this diagram. So as carnallite's buried, it moves from the carnallite stability field in A, where it's being precipitated as carnallite, then with burial, increasing temperature and increasing burial, indicated by those red arrows, moves that system into the carnallite-sylvite association. We move the carnallite-sylvite boundary, we move it to progressively higher values of K as we go from time 1 to time 2. If we have something which was deposited in position A, we actually get it incongruently altering to KCl with a loss, as that equation is showing you, with a loss of the magnesium, the chlorine, and water. So back to this diagram. At a pressure of 1 kilobar, which corresponds to a lithostatic load equivalent to about 2 to 3 kilometers depth, the ion activity product, indicated by log K, of that solution that precipitated the original carnallite at 1 bar, now lies in the sylvite field. And this is the diagram taken from Kohler and others in 1990. This is the diagram that underlines the notion of the incongruent transformation of carnallite to sylvite with burial. And of course, that's going to be a texturally altering system as well. This is the main mesogenetic mechanism that people use to explain the incongruent conversion of carnallite to sylvite that we see in many potash ore deposits around the world. Once again, go back to our potash course if you want more detail on the chemistry of this alteration. Quite often, in areas of predominantly sylvite, because of this alteration and the loss of volume, the loss of the magnesium chloride, and the loss of the water, we see that where we have sylvite passing laterally into carnallite or carnallitite associations, those overlying formations appear to drape into that evaporite stage, telling us that mineralogical change was responsible for stratigraphic thinning. It was not a depositional thinning, but a diagenetic thinning related to the loss of water and magnesium chloride during that transformation. Along with that, we see petrographic relationships between sylvite and carnallite in combination with the stratigraphic evidence telling us that we're not seeing syndepositional sylvite in most cases. We're seeing it as a eogenetic to mesogenetic alteration product for most ancient sylvite. It's a diagenetic product of the subsurface, often reworking from the original carnallite precipitation. In fact, if we precipitate carnallite today, as we saw in the potash course when we looked at brine and potash, there are very few examples where sylvite is a primary precipitate. In the Wendover region, Utah, it is, but generally when we look at where we are forming large volumes of potash salts, they form as carnallite, not sylvite. Certainly in the Dead Sea, that's what we see on both the Israeli and the Jordanian side of those large anthropogenic pans at the southern end of the Dead Sea. Once again, go to the Potash course for more detail. Petrographically, if we come back to the prairie evaporite, which is the main evaporite ore supplying the world's potash from the West Canadian Sedimentary Basin, it looks like some of the carnallite and the sylvite has been transformed from one to the other. Age-wise, argon dates are showing us that they are both younger than the coexisting halite. We also see relatively high rubidium concentrations in those Devonian potash ores in Canada, once again indicating that we are leaching carnallite to leave behind elevated rubidium levels. We can also see sylvite stratigraphically overlying carnallite resin, which is the reverse of that expected depositional sequence if we look at what happens as we go through the bittern salts in seawater. Perhaps most telling is when we look at potassium-argon dates across a range of minerals in ores in the Canadian Devonian prairie evaporite. These potassium-argon dates are showing us that there are a whole range of precipitation corresponding with changes in the magnetic declination. We see a range of precipitate ages across the system. And so you can see there we've got sylvite forming ages ranging from very early, 375.2 million years ago, soon after the deposition of the original carnallite, multiple stages to some as young as dates around 128 million years ago. All of this is telling us that potash is highly reactive in the subsurface. It's undergoing alteration. Typically, carnallites incongruently alter into sylvite to form the sylvite ores. But in some situations, we can also preserve the original sylvite precipitation features as we see in the neogene potash deposits of Spain. For more detail on this, if you're interested, I recommend that you sign up for our online potash course, where each of these topics I've skimmed over has a chapter or a module devoted to it.